All right, let's dive in. Today, we are talking about one of the coolest, literally, challenges in engineering. How do you air condition a skyscraper? Now, if you get this wrong, you're not just looking at a small problem, you're risking a catastrophic failure. But if you get it right, well, it's a masterpiece. So, this is your step-by-step guide to doing it the right way, the code-compliant way. Let's get to it. So, it all starts with this one question, right? How in the world do you get cooling all the way to the top of a 300-meter building, nearly 1,000 feet tall, and do it safely and efficiently? The answer isn't just about bigger chillers or more horsepower. It really comes down to physics. And believe me, the stakes are incredibly high. One single mistake in your pressure calculations can lead to a total system failure. We're talking massive floods and repairs that can run into the millions of dollars. We're going to walk you through the roadmap to make sure that never ever happens on a project you're a part of. Okay, first things first. We have to wrap our heads around the real enemy here. And surprisingly, it's not the chillers, it's not the pumps. It's the simple but immense, crushing force of pressure that's created by the building's own height. So let me introduce you to the main villain of our story, static head. It's really just a fancy term for the weight of the water sitting in the pipes, pushing down thanks to gravity. And the taller that column of water gets, the more intense that pressure becomes at the very bottom. Now, what's really cool is how simple the math is to figure this out. It's a great rule of thumb. For every 10 meters you go up, you gain about 1 bar of static pressure. It's a beautifully simple formula, but man, it has some seriously powerful consequences. So let's just apply that to our 300-meter skyscraper. You take 300, you divide it by 10, and you get 30 bar. 30. That's over 430 psi of constant, relentless pressure pushing on every pipe, every valve, and every coil at the base of that building. And that's before you even turn the pumps on. And this right here, this is the whole problem in a nutshell. Standard, off-the-shelf pipes and components are often rated for PN16, which means 16 bar. But our system is creating almost double that. So trying to run one single pipe loop from the basement to the roof isn't just a bad idea, it's a huge code violation according to standards like SBC 501 and ASHRAE. It's not allowed, period. All right, so we've established that the pressure is a massive hurdle. Now, let's switch gears and figure out just how much cooling power we even need for a monster of a building like this. We're going to start with the classic ASHRAE formula. You take the total area of the building and you multiply it by the load density. Now, that density factor, that takes into account all the heat coming off of people, computers, lights, all of it. And for a 120-floor tower, you can bet that number gets big fast. So after we run the numbers for our example building, we land right around 10,200 tons of refrigeration. And just to give you some perspective, 1 TR is the amount of energy it takes to melt a ton of ice in a day. So yeah, that is a staggering amount of heat we need to remove. But wait, we can't just stop there. We can't design the system to just barely meet the demand. Codes like the Saudi Building Code and major engineering standards from places like Aramco are super clear about this. You have to add a safety margin, usually around 15%, to make sure the system can handle the hottest days and has room for the future. So we add our 15% safety margin, and we land on our final design capacity, 11,500 tons of refrigeration. This is the number. This is what our cooling plant, whether it's our own chillers or a feed from a district cooling plant, absolutely has to deliver, day in and day out. Okay, so we've got our cooling number, and we know we can't use one giant loop because the pressure would blow it apart. So what's the solution? Well, it's actually a really elegant strategy. We're going to divide and conquer by breaking the building into vertical zones. Here's the game plan. We slice the skyscraper into these manageable chunks, say 40 floors each. Then, between each of these zones, we stick a dedicated mechanical floor. And on that floor, we build an energy transfer station. What this does is it creates these completely separate low-pressure water loops that only have to serve their own little section of the building. And the undisputed hero of this entire strategy is the plate heat exchanger. Seriously, think of it like a thermal gatekeeper. It lets the cold from the main water line pass through to the next zone's loop, but it physically blocks the pressure from crossing over. Each zone is totally isolated, hydraulically speaking, and just like that, our 30-bar pressure problem, gone.
So now that we have these neat independent zones, we can basically treat each one like it's its own smaller building. And what that means is we can finally select the right pumps for each specific job without worrying about insane pressures.
To pick the right pump, the first thing we need is its head, which is just the amount of pressure it needs to create. And we calculate that by adding up the static head for that zone only, plus the friction loss you get from water moving through pipes, plus a little extra for a safety margin.
And this is the part that changes everything. Look at this example for our first 40-floor zone. The static head is only 120 meters. You add in friction and a safety margin, and suddenly we only need a pump that can provide 155 meters of head. That's a powerful pump for sure, but it's a standard, readily available piece of equipment. We've taken an impossible problem and made it totally manageable.
Okay, next up, we need to know how much water the pump needs to move. That's the flow rate. For that, we use the standard formula here. We just plug in the cooling load for that one zone in TR and the system's design temperature difference, the delta T, and boom, that gives us our gallons per minute. Now we know exactly which pump to order.
You know, a perfect design on paper is completely worthless if it isn't built right. So this final phase is all about what happens on site. It's about execution, it's about quality control, and it's about making sure the thing that's in the drawings is what actually gets installed.
So let's just quickly recap the absolute cardinal sins of high-rise HVAC design. Trying to run a single loop, ignoring static pressure, using underrated pipes, skipping the heat exchangers. These aren't just little oopsies. These are guaranteed failures that will violate a whole stack of codes and standards. You just can't do it. And to make sure none of those mistakes happen, here is your on-site checklist for success. Every single one of these steps, from the hydrostatic pressure test that proves the pipes won't leak, to the final tab report that verifies you have the right water flow everywhere, each one is a mandatory checkpoint. They're directly linked to codes from SMACNA, ASHRAE, and others. You follow the list, you stay out of trouble.
So let's wrap this up with the one single engineering truth you have to remember. This is it. This is the non-negotiable principle. High-rise buildings are cooled by breaking them into pressure zones with heat exchangers. Any attempt to simplify this, to cut a corner, you are creating massive, massive risk. It's as simple as that.
And that's our journey through code-compliant design. We've hit the physics, the formulas, and the strategy. So I'll leave you with one final question. Now that you have this knowledge, what's the very first component you're going to double, maybe even triple check on your next high-rise project?